Okay, before I start today's lesson, I was thinking about this as I drove in, half an hour myself, to kind of think about how to introduce this lesson. I wanted to use maybe like a metaphor to kind of describe my purpose behind today's lesson. So I do this stuff all the time. I hope you appreciate it a little bit. So imagine that you're trying to put a puzzle together. I was thinking about like when Kinsey Ann, she has these little Disney princess puzzles. And I mean, there's only like 16 pieces, right? Imagine you're trying to put a puzzle together, but you don't actually know what the puzzle's made of, right? Like you don't have the box, and so you're trying to find similar pieces. Does that make sense? And slowly but surely, you find a way to fit, 3 or 4 pieces together, and then all of a sudden, you're going to have a piece that's going to fit in with the 3 or 4 that are clumped together, or more than that, and all of a sudden, you'll be able to look at the puzzle and be like, I know what it is. It's a picture of a dinosaur, or whatever. Does that make sense? Does that analogy fit? And all of a sudden, it will hopefully click, and you'll see the whole picture. Now, you probably won't see the whole picture, but you'll at least know what it's about. And then you'll find other pieces, and you'll be able to attach them to the edges and go, okay, well, this one goes here, and this one goes here, and finally it starts to come together. That's what I feel like this lesson today is like. I've taught you a bunch of, little key pieces of calorimetry, but this one here today is kind of that unifying piece where I feel kind of bad, actually, because I gave you guys an assignment to do, and then I told you, by the way, you can't do it. And that feels to me kind of weird as a teacher to kind of assign something and say, by the way, you can't do it. And you might ask, well, can you just teach me? And then I have to kind of say, well, I want to, I promise, I'm going to, but I feel like I have to do it in stages. You know what I mean? Like first we have to do this, and then we have to accomplish this. And then once I'm certain that you get the concept of this, now we're ready for the next step. Does that make sense? This is that step. I'm hoping that today you'll be able to look at the assignment, and all of a sudden you look at it and go, wow, I really do know how to do every single question because this will tie it all together. Does that make sense? So. The other reason why this one kind of needs to come so late, I mean, I know it's topic 5. It seems like, well, why could you taught us this first? Is that I have to do Hess's law before this one. And that's just, in order for this to make sense, I kind of told you guys yesterday a partial truth. And I do this a lot. And I tell you afterwards where yesterday I said that Hess's law doesn't really have a whole lot of purpose. I mean, and probably for a while in history, that was probably true. Hess, I guess. I don't even know who Hess even was, but when he discovered this principle of like adding multiple reactions together, I'm not really sure in a vacuum on its own how useful it was. I mean, I can give you some examples saying, well, if you're trying to do this equation here, if this one was unsafe or impractical, we could do this one and this one and this one and add them together for the last one. I think that's reasonable. But whoever it was that came up with this concept of using what's called molar enthalpies of formation, to me, this was clever. This was brilliant, and I think it fundamentally changed how we were able to approach this whole unit. Because up until this point, if I asked you to find a molar enthalpy, the only way you could do it was in a lab setting. You would have to use this equation, mc delta T equals like a delta H per mole, and you'd divide by mole. That was like the only way you could accomplish this. And then someone figured out, hey, let's record a whole bunch of delta H numbers in a chart. And I've kind of briefly referenced this chart to you guys. Do you know what I'm talking about in your data books in here? There's a chart in here on page 4 and 5 where there's just numbers upon numbers. And if you understand how to use this chart, it opens a whole new world of being able to find these delta H numbers, but without having to do an experiment to accomplish that. Does that make sense? So I think maybe the best way of showing you this, you guys probably know by now, like I have my notes and then I kind of, whatever inspires me at the time. So you don't have this slide. I know this, I double checked just to make sure. What I want to do is I'm just going to show you a diploma question. And if you guys want to write this down, sorry, I should maybe check that. If you guys want to write this down and look it over here, I'm going to show you how to solve this question first, and then I'll go back to my notes. Does that work? Give me 1 second. Okay. So here's the premise. They've got an equation here about butane gas, and I mean they've written the whole equation out. They've balanced it, and basically the question is, what is the enthalpy per mole? So in terms of ways that we could solve this from a practical point of view, I guess if we had the internet, we could just Google it. we could go type into a Google search engine, what is the enthalpy of the combustion of butane? Right? And it would probably give you some notation that looks like this. The delta H for the combustion of butane per mole, and then it would give you a number, and it would be a negative number in kilojoules per mole. Another option, we could do a test. We could find a butane lighter. We could put it underneath a tin can calorimeter. We could heat up the water inside the can, and we could do kind of an experiment like our last experiments have been like. We would divide by N using that formula. Here's the method I want to show you. So it really has to do with Hess's law. What does formation mean? Make something from what? Its elements. Okay. So what we could do here, and this is a very long way of doing it, I'm going to show you a shortcut in a second, but I could say that right here, I need to form carbon dioxide. Okay, now, by the way, I picked carbon dioxide because it's on the product side. Would you guys hopefully agree that these two items right here, these need to be formed? Does that make sense? What about these guys right here? Do they need to be formed? What would be an appropriate word for the opposite of forming? That works. What did you say? Decomposition is probably the more common word we'd use, like decomp. Okay. But I'm going to focus on these two to start with, and then I'll come back to those two. If I wanted to form carbon dioxide from its elements, what would that look like as an equation? Well, it would look like this. Carbon plus oxygen would form carbon dioxide. That would be an equation that hopefully you'd agree this is a formation equation. According to Hess's law, though, we need to obtain 8 carbon dioxides. And this equation down here does not have 8 carbon dioxides. So we should balance this in such a way that we get 8 carbon dioxides. That makes sense? Sorry, say that up.
Oh, wait, no. Come on.
You're good?
Yeah.
Okay. Now, this reaction up here is a combustion reaction. We don't have a table of standard combustion numbers. But someone really clever thought, hey, let's put together a table of formation numbers. Which means that the number that could go over here, you actually have it in a table. So if you guys have your data booklets nearby, find that inside page there, and find the number for how much energy would happen if you formed carbon dioxide. Got it? Okay, so the number is negative 393.5. So because someone put a whole bunch of numbers together in a table for us, I now know that this number is negative 393.5. That's how many kilojoules you'd get per mole. But here's the problem. Are we making 1 mole of carbon dioxide? We're making 8 moles. So we need to take this number and we need to times it by 8. Does that make sense so far? That means that we now have the carbon dioxide in the location we want. Okay, there's one more thing we need to form. We also need to form water as a gas. So I'm going to write out an equation for this as well. Water as a gas, if you want to form it, would come from elements, and so those elements would be hydrogen gas and oxygen gas. And in order to make this work, sometimes the easiest way of writing this out is just to go with 1/2 an oxygens to begin with. And the reason why I didn't go with 2s everywhere is because I have that same problem. Right up here, I'm supposed to have 10 hydrogens. Does this thing right here have 10 hydrogens? No, it doesn't. So I can fix that. By the way, can you guys kind of see why I needed to build to this step, this idea of being able to double reactions and be able to solidify the idea of what a per mole kind of means? So a 10 goes here, a 10 goes here. This guy right here is now a 5. So now let's go to our data booklets. Someone took the time to write out a big table that has a whole bunch of formation numbers. Find how much energy it would give off if you formed water. Water as a gas, by the way. Make sure you're specific because it does make a bit of a difference. Okay. So then this number off to the side would be negative 241.8 per mole. So hence the times 10 concept. How am I doing so far? Does that make sense? We've now found a way to form the 2 compounds that are going to be formed in this reaction, the water and the carbon dioxide. Now here's where this table's really clever. Hopefully you'd agree that these things right here, they need to decompose. They need to break up. Well, we don't have a table for decomposition. But the reason why we don't have a table for decomposition is decomposing is the opposite of forming. So yes, what you're going to do is you're going to take the number that you find in the data booklet, and if it's negative, we'll just make it positive. That makes sense? So let's try to write out a decomposition reaction for butane. So butane would be the C4H10. I'm going to decompose it into its elements. So that would be a carbon and a hydrogen like this. In terms of initially balancing it, you'd need to do this. But same problem arises that we've had before. This would only be for 1 mole of butane, and our balanced equation requires 2 moles of butane. So double the equation. So now I need for you guys to do is find in the data booklet what the number for butane is as formation.
125.
And that's it. Is it a positive or a negative?
No, it's negative.
Okay. So Sean's already ahead of me. It is a negative 125. We're gonna make it a positive 125 because formation, decomposition are opposites. So this delta H then will become positive 125.7 times 2. And so now we've got this guy in place. Last thought, we also need to try to find a way to decompose oxygen. And this actually becomes a really good talking point here. How do you decompose oxygen? What would you decompose it into? Oxygen's an element already. So we're actually just going to leave it. Okay, so according to Hess's law now, that whole idea of like a system of equations, let's take stock of what we have and see what's left. Here I have 8 carbons. Lo and behold, here I have 8 carbons. Here I have, well actually I need the oxygen, I'm looking for something else. Here we go, here's 10 hydrogens, and here is 10 hydrogens. I think actually everything else is done. Here I have my 2 butanes, which is what I need. Collectively, I have 13 oxygens, which is what I need. 8 carbon dioxides and 10 waters, which is what I need. Does that make sense? So, according to what we did with Hess's law, to find out the answer to my question, I just need to figure out that. So grab a calculator, mine's in my bag, and you guys can beat me to it. So what we need to do is take negative 393.5 times it by 8. We're going to need to add to that a negative 241.8, but that's times by 10. And we're also going to need to add to that a positive 125.7 times by 2. So by the time I'm done, I got the number 5314.6. Anybody else get that? Actually, I got negative 5314.6. Okay, the diploma question though is really, really mean. This would be how many kilojoules there is, not kilojoules per mole. And so if you try to pick this answer right here, this one's actually wrong. Because it wants to know per mole of butane. And how many moles of butane does this reaction show us having? 2. So to make it per 1 mole, we're going to have to cut this in half. Yeah, that last trick is particularly mean. So you should get negative 2657.3 kilojoules per mole of butane. I should even write that, of butane. And so then, that was the answer. Were you able to follow that? Okay, now, we're never going to do it like that again. That's the really long way of trying to accomplish a task. I have a shortcut that we can do to try to make this simpler. But to me, this is the groundbreaking step where once you understand how to use this table, you can answer a lot more questions because you don't have to do a calorimetry experiment to try to find how much energy something gives off. You just need to understand how to use Hess's law, fit together these numbers, and then you can find the delta H number without having to Google it or experiment. This means that now pretty much any question should be answerable. Like if on your assignment I say, find me the enthalpy of some equation, now you have the ability to find that enthalpy. That makes sense? Okay, let's go through my notes then, I guess. Now that I've kind of shown you an example. So, first note here that I wrote down, if you want to try to form an element, you can't really form an element. So you know how like when I did oxygen gas right there and I was trying to look up numbers in the data booklet, you're never going to find a number in here for oxygen because you can't form oxygen. It's an element, not a compound. So that's probably the first thing you need to know. Okay. And then, I mean, you guys probably know this next line. A formation reaction is one where you form a compound from elements. And so, long story short, they've decided, or someone really clever decided, that we should put all of the formation numbers in a table. Not the combustion numbers and not the decomposition and the neutralization, but if we make a table just purely filled with formation values, that's the key to basically doing any reaction. Because there's always in a reaction going to be something being formed, that's going to go on that side of the equation. And there's always going to be something being decomposed, which will be on the other side of the equation. And really, formation and decomposition are really the same thing, just flipped. So all we need is a single table about formation numbers. So, if you see this notation right here, though, which you can just grab out of your data book, that 285.8 kilojoules per mole number, or just kilojoules number, it really implies this equation right here. And if you'd like to, you can even think of it like this. There's no energy in a hydrogen element. We're just kind of arbitrarily assigning it as 0. And there's no energy in an oxygen because, again, they're elements. But if those elements needed to form together to form water, it would release that much energy. Does that make sense in terms of being able to interpret it? So, you may come across this term right here. I've never seen it on the diploma, but I always make sure to just make sure you've heard it before in case they throw it on there. It's called thermal stability. This table can also help with thermal stability. Certain compounds are more prone to decomposing than others. From like an environmental perspective, anybody ever heard of like the Nalgene water bottles, where like if you put water in certain bottles, then they thought it was causing cancer because like the bottle itself is breaking down? You guys ever heard of things along those lines? That's probably the best analogy I can give of thermal stability, where certain compounds, they should possibly decompose into their elements or at least into something else slowly over time. So if something is thermally stable, it means that they won't break up into pieces. And we can actually tell you which sort of compounds are thermally stable based on your table here. Okay, let me see if I can walk you through this train of thought. In order for something to break into pieces, it's going to require energy. Does that make sense? If I want my water bottle to decompose, it would have to absorb some energy in order to do that. Does that make sense? It's just not, yes, maybe it naturally can just do that on its own, but if something absorbs energy, it's endothermic, correct? So in order to decompose something, if you have a very large positive number, it means that it's not going to decompose all that well. Let me say that again. A large positive delta H number for decomposing means it needs to absorb a lot of energy before it can actually decompose. Our table doesn't give decomposition numbers, though it gives formation numbers. So if things are going to be thermally stable, they need to have a large positive decomposition number or a large negative formation number. So the most thermally stable things on your table are the biggest negative numbers. The larger the negative number on your table, the most stable it is. Can I say that one more time? the largest negative number found on your table, those are the elements, or those are the compounds that are the most stable. Okay. The rationale is, as a formation reaction, they would release the most energy. However, if you wanted to decompose them, therefore they would require the most energy to decompose. So if I can do some examples here and walk through them. Sure, yeah. Glucose, sucrose, if you find those ones are the hardest things to just decompose. It's going to take a lot of energy to burn sucrose and to burn glucose. That makes sense? Which is good, which is why it stays for so long, right? Your Rice Krispie cereal that's full of sugar is not going to decompose and lose that sugar for some unknown reason. Does that make sense? Like it will stay. Water.
Shit, I'm hungry. Somebody else? You guys used to eat breakfast in math class.
Thanks, guys. Appreciate it. Okay. Does this make sense? Basically, if they ever ask you for thermal stability, which I've taught this now for 8-7 years, I've never seen them actually do this, but in case they do, large negative numbers on your table are the most stable. Okay. Rationale is they would release the most energy during a formation reaction, so therefore they would need to absorb the most energy during decomposition. Okay, let's move on here. That really is more of a side note. So let's try another example here, and this time around though, I'm going to try to do a little bit of a faster method of solving this question. Let's say that I asked you guys, try to tell me how much enthalpy this reaction here would have. You're going to pick these sorts of questions out really fast because you're going to look at the example and you're going to be like, where are the numbers? Does that make sense? Like as you look at this example, you're like, sure, give me some numbers to work with, and I'll be like, you don't need any numbers. Okay, that's how you're going to know to do this sort of step. So here's how I'm going to solve a little bit faster. Calcium hydroxide, is it being formed? Yes, it's on the product side, so it's being formed. So what I'm going to do is I'm going to look up its formation number in the data book. So calcium hydroxide, its number is negative 985.2. Let's find that. How many of them do I need according to this equation? Just one. So I'm going to write over here a negative 9. Shoot, what was it again? 48.2? 85.2. Okay. Okay, then I'm going to look at water. Is water being formed? It's being decomposed. So what I need to do is I need to find water's value and flip it. Because it's not being formed, it's being decomposed. So water's value as a liquid is negative 285.8. I'm going to make it positive 285.8. And then I think this first example I picked because it's simple. Do we need to times by any coefficients? No, because there's just one of them needed. Last thing here, we need to find calcium oxide. Is calcium oxide being formed? No, it's on the reactant side, so it's being decomposed. So find calcium oxide's number, which is negative 634.9, and make it positive 634.9. According to Hess's law, if we did this whole process of actually writing out every single equation like I did right here, I promise you, all the extra extraneous stuff would cancel. I promise you it would. So we don't actually have to write it out every single time. All we have to do is find these numbers right here, times them by any coefficients, and just add them up. And that's Hess's law. So to answer this question right here, just add these three numbers up. 634.9 plus 285.8 minus 985.2. I got negative 64.5 kilojoules. That makes sense? If we write the enthalpy off to the side like this, does it need to be per mole? No. If I want to make it per mole, what would I have to do? Well, you'd have to divide by the coefficient of whatever it was you were talking about. So if it was per mole of this guy right here, you'd divide by 1. If it was per mole of this guy right here, you'd also divide by 1. This equation is kind of boring. If you wanted to make this one per mole, it would be the same number because all of these things have a 1 in front of them, if that makes sense. But if one of them had a 2 or a 3, we would have to divide by that 2 or 3 to make it per mole. Okay. That's that twist on that diploma question there that would catch a lot of kids. The answer that we calculated was, what, about 5,000 something? And they actually threw that answer in as a distractor to try to mess with you. So just make sure that you're kind of aware about that. That makes sense. Let's try another one. Okay, methane is burned. We want to try to find the standard molar enthalpy of combustion of methane. So you're going to be able to pick out this sort of question real fast. There are no numbers given to you. So that means that you got to do this all with the data booklet. So write out methane's equation. CH4 plus O2 makes CO2 plus water. And you guys should probably know this on your own without it specifically telling you this. But when you combust things, water is in vapor format. Because it makes a difference on this table. I guess I'll throw states of matter in there. I've been bugging you guys about that for years to do that, so I should follow my own advice. And before I go hop into the data booklet, what should I probably do to the equation first, though? And the balancing is important because when I look up numbers in the data booklet, I'm going to have to times by what those numbers are. So we'll need a 2 and a 2. So far, so good. Okay, so now I'll actually start from left to right this time. Methane. Methane's being decomposed, so I'm going to look up methane's number and I'm going to flip it. So methane is negative 74.6. I'm going to make this positive 74.6. I'm going to times it by 1. So therefore I'm going to do nothing. Oxygen. Yeah. Sometimes I find kids will ask me, they'll be like, I can't find oxygen on this table. Like, I don't mean to, like laugh at them or something like that, but I'm like, there's a reason why oxygen is not on the table, because oxygen is not a compound. So if you ever feel like, my goodness, where the heck is oxygen? There is no formation number for it. You can't form it. It's an element. Carbon dioxide, negative 393.5 times by 1. And then water as a vapor is negative 241.8. But don't forget to double it because that's what the recipe calls for. You need 2 of them. And then Hess's law, add it all together. It does, doesn't it? Do you get what I mean, though, when I say that I don't want to throw this at you on day 1 or day 2 because I don't think you're ready for it yet. Like, I really want to help build things up to a certain point so that hopefully today being that last puzzle piece, I'm hoping all of a sudden you see this and go, wow, okay, that works. That's my hope. That's how I try to structure my, not just like my lessons, but just like the order in which I teach things. So, I got negative 802.5. We just need to make sure that we're not sloppy on the last little details here. This number right here that we calculated would be a kilojoules number. But the question asked me for a molar enthalpy. So we need to divide by the moles of something. And since it said it was of methane, we have to divide by the moles of methane. Which in this example here is just 1. So the right answer would be that many kilojoules. Okay. Awesome. That's the concept. Okay, let's see what other extra, like this is where I feel like that puzzle analogy, I don't know what it makes sense to you. It makes sense to me. Or now that I've kind of, you see the big picture here, now let's put some pieces around the edges then. Fill in any details you need. So, here's a picture, kind of showing the same sort of concept. I'm almost willing to wager, I'll probably wager money. You're going to see a graph on your diploma. Like they love throwing that on there. Where they'll show you, like, here's some stuff up here, here's some stuff down here. Make sure you watch those coefficients really carefully. This is a 1 and a 2 and a 1 and a 2. If they had doubled the reaction, they would need to double the energy change. Does that make sense? Now, the difference between this number and this number, I'm guessing if you subtract them, we should probably do that. 877.1 minus 74.6, yeah, is 802.5. And it's negative because it's going down. So they're probably going to give you a graph. I don't know how they'll phrase it, but I could see them not giving you this number, and they might give you these numbers here, and you have to use that to get a number like that. Oh, actually, I guess I'm done. I don't remember what I have in my notes anymore. Make sense? Okay. You should now be able to do a lot more. If I give you calorimetry data, like in your assignment on question 6, you should be able to do that. If I give you multiple equations, like on question, Devin, you did it yesterday. What was that question? Number 5. You should be able to do that. But pretty much almost every other question you should be able to solve now, because if it feels like you're lacking numbers, you have them. That's what the table's for. Okay. So everything's kind of hidden in here. And you're going to get a lot of questions where you're going to have to use this table. It's kind of mean in a way, but from my perspective, I think whoever thought of this was really clever. Because this is going to save you a lot of time, right? Rather than every single time from a chemistry point of view, rather than having to actually go out and perform an experiment every time, if you just have a list of numbers that have been pre-calculated, that should be sufficient to really solve any problem. Okay, why don't you guys take a break in a few minutes here, take the rest of today's class to work on stuff. Tomorrow we're going to do another lab. So the concept behind tomorrow's lab is I really want to try to focus on the Hess's law concept. We're going to burn magnesium, and we're going to try to find magnesium's enthalpy of formation. You know what, actually, let's talk about this now since we're talking about this. What would burning magnesium look like as a chemical equation? Here's magnesium. How do you burn something? What do you need? Oxygen. Yeah, you need oxygen. What's that going to turn into? Okay, here's one of the cool things about this particular equation. This equation is a combustion reaction and a formation reaction. Say that again. This equation is a combustion reaction and a formation reaction. It's being combusted because it's burning with oxygen, but it's also being formed if you approach it as the formation of the magnesium oxide. Therefore, you guys should know what the right answer is by just looking it up, because you have data. How much enthalpy should we get when we form magnesium oxide? Negative 601.6. Does that make sense? So we actually already know what the answer should be by looking at our data booklet. What we're going to do tomorrow is, I can't actually put magnesium oxide as a strip of metal. Have you guys seen the burning of it before? Has Lab done this? If he taught you, or I heard about that one year. Yeah, it burns really hot, really bright, and it only lasts for like 10 seconds. There's no reasonable way that we're going to get effective data from burning that underneath a tin can. But what I can do is I can show you 3 other reactions where we'll do reaction 1, reaction 2, reaction 3. A bunch of stuff will cancel, and we're going to manipulate it and make this equation right here. And if things go well, I've had classes before where they get like 605 or 592, somewhere in the near ballpark for that number. So I'm hoping tomorrow's lab will help solidify this concept too. So, questions, comments, concerns, conundrums, all the C words, keywords there. You guys good? Did I explain that well to you? All right, cool. Take a break and then work on something, I guess. So let me know how I can help.